Hello and welcome to EngPhys 3 BA3 Lecture 12, Digital Electronics 1. This is going to be the first of 3 lectures on Digital Electronics, Chapter 7. So here we're going to do Chapter 7.1 to 7.4. First we're talking about Combinatorial Logic. This is going to introduce logic gates and look at some truth tables and all that. So here we have the basic logic gates. This is a NOT gate, an OR gate, AND gate, XOR, and a NAND gate. These are not all the gates, these are just some of them. So what we're missing a NOR gate, which would just be an OR gate with the little circle at the end of it, and an XNOR gate, which would be an XOR gate with the circle at the end of it. So the circle means invert. So you can think of it as inverting whatever is going through the path that the circle hits. So that's why this is an inverter. Without the circle, this would just be an op-amp follower circuit, which you could use to fix impedance levels like we did before. Okay, so here's some truth tables for these. You're probably familiar with this. This is review from second year for most of you. So an AND gate just outputs a 1 if and only if both the inputs are high, otherwise it outputs 0. An OR gate outputs a 1 as long as one of the inputs is high or both of them. An XOR gate is an exclusive OR. It outputs 1 only if exactly one of the inputs is high, either one. If they're both high or both low, it outputs a 0. And the AND gates just do those things, but the opposite. So a NAND gate, because an AND gate puts out a 1 only if both inputs are high, a NAND gate puts out a 0 only if both inputs are high. So if both inputs are anything except both high, so if you've got like a 0, 0 or a 1, 0 or a 0, 1, then the NAND gate will put out a 1. If you've got 1, 1, the NAND gate puts out a 0. There's 16 total possible logic gates that have 2 inputs and 1 outputs. Not all of these are commonly used enough to have names. So here we go. AB is 0, 0, 0, 1, 1, 0, 1, 1. These are the examples of what we could have for the 4 different inputs. And for these 4 different inputs, what is the output state? We could have either a 0 or a 1 for any of these possible inputs. So it's kind of like we got 3 different numbers, all with a possible value of 0 or 1. So how many different gates do we have? Well, you might look at that and say, oh, well, there's 2 to the 3, and so there's 8 possible gates. But actually, that's not the right way to think about it. Actually, what's going on is we've got, since there's 4 different possible states for A and B, that means that for each of these states, we have an output, and that means there's 4 outputs, 4 output states to look at, and each of those output states could be 1 or 0. So the actual answer is 2 to the 4, because there's 4 output states to consider in total. So all of the different permutations of that would be 2 to the 4, the 16 different gates. Okay. Gates are assumed to have perfect inputs and outputs. You can take the output of a gate and wire it into as many inputs as you like. So perfect inputs means infinite input impedance, and a perfect output means 0 output impedance. Because of that 0 output impedance, this is logically ambiguous. It's not clear what the input here would be. You can't have 2 gates going together like that. If you want to combine them, then combine them with some other gate setup. So like, what do you mean here? Do you mean that do you want this to go high if either one of these is high, or if only both of them are high? So put in another logic gate here. If you were to actually hook this up, then what you'd really get is the circuits would fight each other if they're ever in a different output state, or even if they're in the same output state, but they have a different idea about what plus 5 volts or 0 is, then these in general would be could fight each other and run a whole bunch of current that you don't want heating up and burning out. All right, you can actually make these gates. Like what is a gate? We haven't been analyzing this. There's ultimately just like resistors, capacitors, diodes, and the transistors that we were dealing with. Those are all the fundamental components. So how can you make a logic gate? What is that? Well, there's a couple of different ways. You can use BJT, transistor logic, MOSFET and resistor TTL, which we haven't talked about yet, or CMOS. So CMOS is the preferred way. This has really low quiescent current. It does use twice as many MOSFETs as the MOSFET and resistor one. So here's another way that you could build a similar kind of logic circuits. Like, let's look at how this thing works. If Vi is 0, then this FET is closed off, and so VO is going to compare these two resistors. You've got some finite number and infinity, and so VO is going to be pulled to Vs. But if Vi is on, if it's a high, then VO gets pulled down to 0, and because this resistor goes to much less than this fixed resistance value. The disadvantage of using this MOSFET setup is that it drains current. So when we've got this as an on here, then we're dropping Vs over R. You can make R big, but if you do that, then the circuit takes longer to switch. So this is kind of a trade-off. It's not necessarily the best way to do it, and for most low power options, CMOS is better, and that's why the CMOS has dominated circuits since 1976 in terms of CPUs anyway. Okay, exercise 7.2. This is going to be pretty challenging. It's a design exercise. Let's see if you can figure this out. Use NAND gates to construct an OR gate and an XOR gate. So it turns out that you can use that the NAND gate is so versatile that you can use it to build up any of these any of the other gates that you want. So you can just combine NAND gates only and make all of these things. So for instance, how do you make a NOT gate out of a NAND gate? Well, all you do is you take one of the pins and you wire it to high. Let's consider how that works. If input 2 is always a 1, so that's this column right here, then you can see the output is going to be the opposite of whatever input 1 is. So it's not input 1 as long as input 2 is high. And that's how you can use a NAND gate to make a NOT gate. You can also use a NAND gate to implement all of these other gates. So let's give that a shot. Let's try to use a NAND gate to make an OR gate and then an XOR gate. All right, well, here's the OR gate using NAND gates. How does this work? NAND outputs a 1 unless both its inputs are high. So if you put not A and not B as the inputs, then it will output a 1 unless A and B are both low, which is what an OR does. Okay, the XOR, more complicated, outputs a 1 if A and B are, if A or B are high, but not if both are high. So we need A or B to be true, but we need A and B to be false. So we need A or B and A NAND B. So A and B has to be false. So what we're going to be doing is, how do we AND using a NAND gate? Well, if we NOT the output of a NAND gate, then we've got an AND. So this here is an AND gate. Here's NANDing A and B. And wait a minute, we're using an OR gate. That's cheating. Ah, not so, because in the last part, we figured out how to make an OR gate with a NAND gate. So just replace this gate with this one here, and then we've got only NAND gates constructing an XOR. You could try this out for some of the other ones if you feel ambitious. Okay, determine the output of this circuit for all the possible different inputs. We've got 3 different inputs, this one, and this one. So make a truth table of all those inputs. There's 8 possible inputs, and figure out what the outputs are. Okay, so here we've got the input to the OR, the inputs, and the first 2 inputs to the AND. So you should get something like this. Output from the OR is not going to be a 1 unless either this OR has an input of 1, or this AND is a 1. So here's where the AND is 1, there that's a 1, and then all the cases where the OR is a 1, that outputs a 1. Now what about the final AND? Well, all we're doing when we wire both of them together is just following whatever was on this line. So that just is going to output a 1 whenever the AND is inputting a 1. And sure enough, that's when A1 and A2 are both a 1. Design an AND circuit using only 2 MOSFETs. So because we only have 2 MOSFETs, this is going to have to be that MOSFET resistor logic business. Okay, so here we go. We've got 2 MOSFETs. What kind are these? These are N-channel MOSFETs. You can tell which kind of channel it is by looking at the arrow. The arrow tells you, a way to remember that is the arrow shows which way the charge carriers are going to flow in the channel creating region if you put a high voltage there. So if you put a positive voltage there, it means that you're going to have charge carriers flow in. So that means that they're N-type, and so this is an N-channel MOSFET. The P-type MOSFET has arrows pointing out, which means positive voltage makes the channel, removes the channel, removes any channel that was there. Okay, now back to the issue at hand. Why is this an AND gate? Well, it uses two MOSFETs. Check. Does it implement an AND function? If they're both high, then it pulls it up to Vs. If any one of them is low, though, then this can't conduct, and so VO goes to ground because these MOSFET resistances are dominant over this resistance here. All right, next section, bistable circuits and dynamic memory. So let's analyze this circuit. This is called the latch. What this does, first, let's guess a state of the circuit. So let's suppose that Q is high. Okay, so Q is a 1, which means we've got a 1 here, and if these are disconnected, then no current is flowing into the gate. They've got infinite input impedance. So this means this is a 1 as well. So 1 and 1 makes Q bar a 0. And then one of the inputs to here is 0, so we don't need to care what this is, but it's high anyway. And so the output stays a 1. Okay, so if this is a 1, then that feeds into here, and the output of that feeds into there, and keeps this at a 1 and this at a 0. Suppose this was originally a 0. Okay, now one of the inputs here is a 0, which makes the output a 1, and then this is a 1, this input's a 1, and so this stays 0. So either one of those two states is consistent. If Q was originally a 1, then Q bar, meaning not Q, is a 0, and vice versa. All right, so whatever state it has, it's going to hold that. Let's see what happens when we push down S or R, called the set and reset buttons or pins. So set, if you put that to a 0, then now one of the inputs here is a 0, which forces the output high, and then we've traced that before, it makes the other output a 0. If we push this down instead, then one of the inputs for this NAND becomes a 0, which forces this output Q bar to high and forces Q to low. Okay, so if you take Q as the output and Q bar as the inverted output, then hitting the set pin makes the output go high, regardless of what it was. Hitting the R pin, that is putting R to 0, makes the output go low, regardless of what it was. Okay, so this latches on to whatever input you have. Like if you set S to low, you connect the S pin to ground in order to set it high originally. It'll just latch that value and hold it still. And if you put R to ground by closing this switch, it'll latch the output Q to low and Q bar consequently to high. One immediate application of a latch circuit is a switch debounce. If you close a switch in a circuit, then whenever you make the metal contact the other piece of metal, it's going to bounce off a little bit. Like it doesn't go from a state where it's not touching at all to a state where it's touching forever. If you place metal in contact with another one, it's going to bounce. Imagine hitting like a one baseball bat with another one. As they come into contact, it's like a ting, 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 ting. They're going to take a little bit of time to come into contact on some kind of small scale. So then what's going on, so you can fix that, because that might wreak havoc on a circuit by using this latch circuit like this. So we've got that the switch, we can switch it from B to A. When it's at B, the output is going to be a 0, and then as we switch it to A, the output is going to be a 1. Now, why is this better than just using a regular switch? Well, it gets rid of that bouncing problem, so it debounces from that metal on metal contact thing. Because of how the latch works, as soon as this touches A, then Q is going to be a 1 until the switch goes back and touches B. So even if it touches A and then disconnects from A as it sort of comes into resting on A, Q is going to switch to 1 on the first time and then just hold there regardless of our fumbling around with the switch over here, unless we bring it all the way back to B. So it gets rid of some metal on metal bouncing problems. All right, the basic building blocks of digital beyond gates are kind of combinations of gates. So here's the next level up in the hierarchy. These are flip-flops or flops equivalently. We've got probably the simplest one, a D flop, and a little more complicated, a JK flip-flop. JK has 2 inputs plus a clock, and the D flip-flop has just a D input and a clock. D stands for data. J and K do something a little bit more complicated. We'll get to that in a second. Notice that they've still got a set and reset input and two outputs, the regular and the inverted output. So the set and reset will, so wiring up set will set Q to high, and wiring up reset will set Q to low. Q bar is always the opposite of Q. These are not designed to behave well if you put S and R connected at the same time. So if you put S to high and R to high. Unlike the latch circuits that we were looking at before, where the idea was to put the S and R pins to ground, in the standard flip-flop design, S and R are normally pinned to ground, and they only do something when you put them to 1. Okay, so if you put S to 1, then it's going to make the output fixed to 1. If you put R to 1, it's going to set the output to 0, regardless of what it was in either case. If you leave S and R at 0, then the output's going to switch depending on what's going on at the main inputs, then the D or JK, as the case may be. And in that case, the output only switches on the clock cycle. If both S and R are 1, then the output's indeterminate. So don't put S and R to 1 at the same time. Okay, so let's look at what exactly does the D flip-flop do? Well, all it does is whenever the clock is a 1, it'll pass, whenever clock and D are 1, it'll make Q equal to a 1. If clock is 1 and D is not 1, it'll make Q equal to 0. So whenever clock goes to 1, it passes D over to Q. And the inverse of that goes on to Q bar. Unless S or R are set, in which case those override it. Here's one way that you could make a D flip-flop. Let's consider the case when S and R are both 0, so the normal operating state. In that case, these NOR gates just behave like NOT gates. So we're passing NOT this input over to here, and NOT this input over to here. When clock is low, then both of these are outputting a 0, and so not 0 is 1. We're getting a 1 to both of these inputs here, which is just like when we were pinning the bottom parts and top parts, like the other inputs to the latch to a high. Okay, so we've got 1 at both of those inputs, and that means it's just holding its output. Now, what happens when we put a 0 up here? Well, either by putting the set pin to a high, or this and to a high, because clock and data are high. So if clock happens when data is up, or when we put set on, then we get a 0 here, and that pins this to a 1. Right? If one of these goes to low, then this goes to 1 from whatever it was at. Conversely, if we get a 0 here, either because we put the reset pin to a 1, or because clock went high when data was low, then we put this to a 0, and that puts the output Q bar to a high, which conversely puts Q to a low. A JK flip-flop, on the other hand, is more complicated because we've got two inputs. Here's how it works. If both J and K are 0, then when the clock triggers, it doesn't, so unlike the D flip-flop where it just sets whatever data is whenever clock triggers to the output, on the JK flip-flop, if both the inputs are 0, it just leaves the output alone. This lets you more easily use it like a latch. If J and K, so if K is 1 and J is 0, or if J is 1 and K is 0, if they're different, then it sets the output to whatever J was. That's a good way to remember it. Now, what if J and K are both 1? In that case, it sets the output to the opposite of whatever it was. That's useful. So you can use this to flip-flop the output, which is where the name comes from whatever the number, whatever output it was, to the opposite of that. JK is a very versatile digital building block. This analysis notwithstanding, always read the datasheet before using a flip-flop because a lot of aspects can vary from one to the next. For instance, we looked up here at the latch behavior, and this was so in this early version of the latch, we had R and S operating when you put them to 0, but the flip-flops designed it when you put them to when you put them to 1. So always double check things with the data sheet, just in case your manufacturer is doing things differently. Here's a question. Hook up a JK flip-flop to replace a D flop, and then to try to replace a latch. So we said, like, is there a way to use this like a D flip-flop or like a latch? Well, for the D flip-flop, all you do is put the data input to J and not D into K. This way they're always, J and K are always going to be different, and so it's going to just set J to the output, and J is D, so now it's operating like a D flip-flop. For the latch, all you do is ground J and K. In that case, it'll just hold the output and just respond to the set and reset pins. Registers, the concept of information. A register is a connected set of memory latches that holds binary values and operates on them. So here's a shift register made from D flops. Here's how this works. The clock, when the clock goes high, it's going to take the input here, gets passed onto D, and then it doesn't get passed immediately onto the next D. What happens instead is the output of this one gets passed to this one, and the output takes a little bit of time to change. Since the clock is wired to all of these, they all get triggered at the same time. They all respond on the rising edge. That's what this little arrow to the right means. As the clock goes high, then it passes this information over to the. It looks at whatever information is on the D, and then after some slewing time inside, maybe 5 milliseconds, it'll pass it over to the right. So when the clock goes high, this input looks at whatever was originally there and then starts passing that data over. If this changes at some point over the next 5 milliseconds, this flip-flop doesn't care. It's going by the input it had as soon as the clock went high, which is what this output was. Similarly for this one and this one. And so what this does is it just shifts all the values one to the right. The Q's are outputs, not inputs. So if originally you had, say, 1, 1, 0, 0, and then you input a 0, the input is a 0 and the clock goes high, then it'll go 0, 1, 1, 0. On the next clock cycle, if the input's still 0, it'll go 0, 0, 1, 1, and then on the next clock cycle, 0, 0, 0, 1, next one, 0, 0, 0, 0. So you see over time this kind of propagates the data through in a wave. That's what a register does. This is a shift register made from D flops because with every clock cycle it shifts things one over. Okay, information is associated with representation. States like Q equals 1 or Q equals 0 from a flip-flop don't inherently contain information until you map them to some state of the external world via code. So you have to use code to read what these values are and use it to make some kind of an understanding of the external world. So a lot of different ways you can do this to map information to the external world, or vice versa. You can use bits as base 2 numbers. 8 bits are 1 byte. 1 byte has 2 to the 8 possible states and can represent numbers from 0 to 255 or from negative 128 to positive 127 if you use them as signed numbers. We'll look at this soon when we do binary addition in the next lecture. Mapping bytes to letters and symbols in English using maybe ASCII, treating bytes as commands or instructions to be sent to electronic circuits, all kinds of ways that you can use these to represent information. We're not going to get very heavy into information theory in this class. Okay, suppose that the Q bar output of a D flop is wired back to the D input from the same flop. Determine the output of the flop in this case if a square wave is sent into the clock input. And what might you use this for? So if we wire the inverted output back into the D input of a flop, then every time the clock goes high, the output is going to switch. So it just inverts every output, but that doesn't mean that it's completely useless. So it doubles the period of the input clock. So it's only going to trigger when the input clock goes high. Once the input clock is high, it stays the same, and then the input clock goes low, it doesn't care. The input clock is low, it doesn't care. Input clock goes high again, it swaps. So every time the input clock goes from high to low to high again, it's going to switch from either low to high or high to low. So it has double the period of the input clock. It also produces a square wave.